This is part 2 of our thermochemistry unit, and we're going to talk about something called Hess's law today. So basically all you need to remember from the previous part is that chemical reactions have an associated delta H, which is the enthalpy change or heat change of that chemical reaction. So Hess's law sounds kind of strange when you just read the law, so let's see what it says, and then we'll explain it. So it states that the energy change in an overall chemical reaction is equal to the sum of the energy changes in the individual steps comprising it. And this is all based on the law of conservation of energy. So really quick, a very simple example is, let's say you do like a two-step process. First you go up some stairs, and then you go down some stairs, okay? So you start here at point A, and you go up the stairs and then down the stairs, and you end here at part B, okay? That's one way to get from point A to point B. Another way to get there is just avoid the stairs, and if it's just up and down, just don't go on the stairs, just go from point A to point B. The main idea is that either way, your distance traveled is the same. It's the distance here from point A to point B. If you went up the stairs and then down the stairs, they kind of canceled each other out. So that's basically what Hess's law says, is that there's more than one way to get from point A to point B. So here's an actual chemistry example of Hess's law. This is basically a two-step process. Here's step 1 and here's step 2. So step 1 says A and B turns into C, and that has a delta H of negative 34. Step 2 says then C and B turns into D, and that has a delta H of negative 87. If you consider both of these steps together, the first one produced C, and then the second one used it up. So since it's on both sides of the arrow, we kind of cancel it out. So C wasn't really there in the very beginning or the very end, so we don't consider it. So what's left over is A and two B's are my reactants, and they produce D because that's the only product we had. So that's this chemical equation here, A and 2B producing D. So if these two individual steps add up to this overall reaction, the two individual delta H's add up to the overall delta H. So negative 34 minus 87, if you add those together, gives you that. So again, the main idea says that, let me get rid of all this ink here. If you add two chemical reactions together to get a new chemical reaction, you also add their delta H's. That's Hess's law. So again, the law says that the energy change of an overall chemical reaction is equal to the sum of the energy changes in the individual reactions comprising it. So again, the sum of these two reactions here formed this reaction, and therefore the delta H of that reaction is the sum of the two steps that made it up. Here's another kind of analogy visual. There's two different ways to get from campsite A to campsite B. You can take the short direct way, or you can take the long winding way, but either way your altitude change from 1,200 feet to 4,800 feet is the same altitude change either way. Okay, here's another visual, again with an actual chemical reaction. This is your starting point here with nitrogen and oxygen. This shows that if you have step 1 that requires energy, and then step 2 that releases some energy, the overall change is that right there, okay? So step 1 was 180 kilojoules. That was going up, so it was positive, endothermic. Step 2 was exothermic, negative 112, exo, okay? So because it was more endo than it was exo, the overall change is positive, or endothermic, okay? All right, here's another pretty simple example here. So given the fact that X turning into Y releases 40 kilojoules, and X turning into Z releases 95, we want to figure out the delta H for this reaction turning Y into Z. So the way I think of these problems, these up here are kind of like the puzzle pieces. They're the pieces I have to work with, and this down here, this equation, I call it the big picture. So somehow we need to rearrange our puzzle pieces to put them together to give me the big picture. So what I do is I look at my big picture, and I see that I need Y on the reactant side. In my puzzle piece, Y is actually on the wrong side. So what I'm going to do is I'm going to take this entire reaction here, and I'm going to flip it. And what that means is I'm going to change the reactants and products and turn it around and say now Y turning into X. Well, what do you think that's going to do to the delta H? it's no longer going to be exothermic, it's going to be endothermic. So I'm going to change the sign. So it's now going to be positive 40 kilojoules. I go back to my big picture now and I see that I need Z as a product. Well, Z is already a product in my puzzle piece, so I'm going to just rewrite that one as is. So X turning into Z, leave the delta H alone. It's still negative 95 kilojoules. So I've rearranged my puzzle pieces to where I think they should add up to give me what I want. So I just do the adding now. So Y turns into X and X turns into Z. If I consider the arrows as my dividing line, I cross out anything that was on both sides. So I cross out my X's, and I'm now left with Y turning into Z, and that's what I wanted. So I do the same thing to my delta H's, I add them together. So 40 minus 95, my overall delta H is negative 55 kilojoules. So that's the main idea here, is you rearrange your puzzle pieces as needed to make them add up to give you the big picture that you want. So here are the rules for rearranging those puzzle pieces. First is you have to decide how to rearrange them, okay? You might need to flip it, or you might need to multiply it by something. If an equation has to be reversed, so that's what we did in that previous example here, step 2, or rule 2, if an equation has to be reversed, you reverse the sign of delta H. So you can just switch between endo and exo by switching between positive and negative delta H. The next possibility, if the equation has to be multiplied to get a certain coefficient, you multiply the delta H by that same thing. So let's say you needed like 2x, and you had x turning into y, being a delta H of 40. If you needed 2x, you would multiply it by 2, so you multiply the whole equation by 2, so the x and the y, and your delta H you also multiply by 2, so now it would be 80. After you've rearranged things, you just want to check and show some work to make sure that everything cancels out to give you exactly what you want. And my strategy here is that it's often helpful to begin your work by looking at the big picture, by looking at that equation of what you want it to add up to. So that's how I'm going to work all of these problems. So let's look at, well, that one we already solved. So we got negative 55. So let's try another one. Here's some real chemicals. Given these puzzle pieces, okay, so we have a bunch of phosphorus and oxygen, both of them are exothermic. We're going to solve for the delta H of this reaction here, okay? So we go step by step, chemical by chemical, in the big picture and try to get stuff in the right spot. So for my final reaction, I want P4O6 on the reactant side. So the only place it shows up in my reactions is up here in reaction 1, but it's on the wrong side of the arrow. So this reaction here, we are going to flip it. So I'm going to rewrite it down here, flipped around. So P4O6 becomes P4 plus 3O2. And what do you do to the delta H if you flip the equation? You change the sign, so it becomes positive 1640.1 kilojoules. Okay? So P4O6 is taken care of. Next I come to oxygen. Do you see how oxygen shows up in 2 reactions? Typically those are going to take care of themselves, so I'm not going to worry about that. We're just going to hope that the oxygen works out the way it's supposed to. Okay? Let me erase some of the junk I have up here. Alright, we go back to our big picture and we see that we want P4O10 on the product side. So the only place it shows up is in reaction 2, and it's on the right side of the arrow, and it has the right coefficient 1. So I'm just going to rewrite that one the same. I'm going to write keep. So P4 plus 5O2 forms P4O10. Didn't change the reaction, so don't change the delta H. That's negative 2940.1 kilojoules. So the P4O10 is good to go. So I've got 2 out of the 3 reactions, 2 out of the 3 chemicals from my big picture in the right spot. If you get all but one in the right spot, the third one's probably going to take care of itself. So we're going to just check it out now and make sure everything added up the way we wanted. So remember, your arrow is your dividing line. So we're going to cancel anything that shows up exactly the same on both sides of the arrow. So in this case, that's going to be the P4, so it just goes away completely. Okay? Now the oxygen doesn't go away completely, but we do have some oxygen on both sides, so we're going to get rid of as much as we can. We can get rid of 3 oxygens from both sides. So this one goes away completely. And the 5, we subtract 3 and it becomes a 2. Well, guess what? That's what we wanted, okay? So let's see what we have left. We have P4O6, we have 2 oxygens, and on the product side we have P4O10. So we have everything we wanted, so we write our final answer, P4O6 plus 2O2 becomes P4O10. And my delta H is going to be the sum of what I'd written over here on the side. So I'm going to switch to my calculator real fast. And we're going to add those up. So 1640.1 minus 2940.1. So our final delta H is negative 1300. So our answer is negative 1300. I'm going to do 0.0 kilojoules. That's the right number of sig figs. It should go to the same place value as the ones that you added up. So that's our first example of Hess's law. All right, here's our next example. Again, we're given 3 reactions. I'm going to call them our 3 puzzle pieces in this problem here. And what we want to find is the delta H of this equation down here. So this is our big picture. Big picture. So that's where we start, by looking at each chemical. We just basically go through. So we start with C2H4. Where does it show up in the puzzle pieces? It shows up in the third one. It's right here. So we ask ourselves 2 questions. First, is it on the correct side of the arrow? And the answer here is no. So this reaction needs to be flipped. We also ask ourselves, does it have the correct coefficient? It does have the right coefficient. It's a 1. So I'm just going to rewrite that equation 3 flipped. Okay? So C2H4 becomes 2 carbons plus 2 H2s. And what do you do to your delta H if you flip the equation? You change the sign. So it becomes negative 52.3 kilojoules. So I'll go back to my big picture, and the C2H4 is completely taken care of. Next, I come to fluorine in my big picture. Well, do you see how fluorine shows up in 2 reactions? I don't know which one to mess with, so we're going to hope that it takes care of itself. That's going to be the 4th one. You know, we try to get 3 out of 4. Let that one take care of itself. So next we come to 2CF4 carbon tetrafluoride. So where does that show up? CF4. It's in reaction 2. Is it on the correct side of the arrow? Yes, it is. It's on the product side. Does it have the right coefficient? No, it does not. It needs a 2. So that entire reaction is going to get multiplied by 2. So that's how I'm going to rewrite it down here. So it becomes 2 carbons plus 4 fluorines becoming 2 carbon tetrafluorides. And so remember, whatever you do to the reaction, you do the same thing to the delta H. So we're going to take this negative 680 times 2. So let's see. Negative 680 times 2. Negative 1360. So negative 1360 kilojoules. Okay? So the CF4 is now taken care of. Finally, 4HF, our last chemical we need to deal with. HF shows up in the reaction 1, and it's on the correct side of the arrow, but again, the coefficient needs to be multiplied by 2. I want to have a 4 on HF, and I only have a 2 on HF. So this equation here is going to get multiplied by 2 all the way through. So I'm going to write it down here. So 2H2 plus 2F2 becomes 4HF, and my delta H, same thing, multiplied by 2. So negative 537, negative 537 times 2, negative 1074. All right, so I've got 3 out of my 4 chemicals taken care of. We hope that the last one takes care of itself. We'll find out. So it's time to cancel stuff out on either side of the arrow. So here's our kind of dividing line. So what shows up on both sides of the arrow? Exactly the same. 2 carbons, so get rid of those. And 2 H2s, 2 hydrogens, get rid of those. And nothing else cancels. Everything else just is going to add up. So I'm going to go to my highlighter and see what's left over. So the C2H4, that's what we wanted. There's our 6 fluorines together, 2 CF4s and 4 HFs. So everything added all together. So we're going to rewrite our final equation here. So C2H4 plus 6F2 becomes 2CF4, 4HF. And we added the equations together, so we add the delta H's. So let's go to our calculator and see what we get. Negative 52.3 minus 1360 and minus 1074. So my final delta H is negative 2486.3. For sig figs, my answer can only go to the tens place. So negative 2490. So negative 2490 kilojoules is my delta H. So that's my answer. So again, the main idea is you figure out how do you rearrange the equations to give you a big picture. You do the same thing to the delta H's, and then when you add the equations, you add the delta H's. That's your final step. Alright, so here's another fairly easy one for us to tackle. We only have 2 puzzle pieces in this one right here, and we're trying to solve for this equation down here. So again, start with your big picture. We want 2 sulfurs on the reaction side. So which reaction does sulfur show up in? Sulfur shows up here in the first one. It's on the correct side of the arrow, but it needs a coefficient of 2. So we're going to multiply that whole equation through by 2, and we're going to multiply the delta H by 2. So we're going to rewrite it as 2S plus 2O2 becomes 2SO2, and the delta H also multiplied by 2. So negative 297 times 2. Negative 594 kilojoules. Okay, so that took care of itself, or that's taken care of. The oxygen shows up in both, so let's hold off on that one, let it work itself out. I need 2 SO3s on the product side. Well, look at that, 2 SO3s on the product side, that's the only place it shows up. So I'm just going to write keep on that one, and I'm going to rewrite it. So 2 SO2 plus O2 becomes 2 SO3. Delta H also remains the same, negative 198 kilojoules. So we add the equations together by canceling stuff out on either side of the arrow. So what shows up on both sides of the arrow, completely identical, what would cancel? In this case, it's going to be the 2 SO2s, completely gone. And so we think about what's left over. I have 2 S's, that's what I wanted. I have 3 oxygens, there's 3 oxygens there, and I have 2 SO3s. So I'm not going to rewrite the total equation, but all of that adds up to what I wanted. So now I'm going to add my delta H's together, and that's going to be my final answer. Different color ink here. Alright, so I'm going to switch to my calculator. Negative 594, that's what I already have there, so I'm going to take that and subtract 198. So negative 792. Delta H for the overall is negative 792 kilojoules. Okay, so those are some basic Hess's law problems. We're going to try one more. This one's a little bit more challenging, so really follow along here. We're going to follow the same basic strategy though, okay? So we're trying to find the delta H of this equation here. Start with your first chemical from the big picture, 2 boron solids, okay? So kind of scan through overall these puzzle pieces. The only place that boron solid shows up is right there. And the good thing is it's already on the correct side of the arrow with the right coefficient. So I'm just going to write that I'm going to keep that one, okay? So 2 boron solids plus 3 hydrogen gases becomes B2H6 gas. Delta H didn't change, so that's at 36 kilojoules, okay? So the 2 borons worked out perfectly, and I used that equation number 4. Next, I get to 3 halves oxygen. You can have fractions, that's fine. And see how oxygen kind of shows up in two separate places? We're going to let that one hopefully work itself out. We'll see what happens. B2O3 solid. Where does that show up? B2O3. It shows up right here in equation number 1. It's on the wrong side of the arrow with the right coefficient. So I need to flip that equation there in my work. So 3O2 gas plus B2H6 gas becomes B2O3 solid plus 3H2O gas. My delta H is also flipped, so negative 2035. Okay, so I've used equation 1 and 4, and I've gotten 2 out of my 3 things in the right place. But if I stop there, do I have anything that cancels out so far? I have the B2H6, so that's good, because I don't want that in my final answer. But I've also got some hydrogen and some water that I don't want in my final equation. Let's deal with the water. So you have 3 H2O gases on the product side. I need to have another equation written where I have 3 H2O gases on the reactant side so that they'll cancel. So where can I get that? I can get that in equation 2. See how I have another H2O gas there? But it's on the wrong side of the arrow, and it needs a coefficient of 3. So I have to flip it and multiply by 3. Okay? So delta H, I'm going to do the same thing. I'm going to make it negative and multiply by 3. Okay? So let's rewrite that equation there backwards. So 3H2O gas becomes 3H2O liquid. So just kind of check that out. I've taken equation 3 and flipped it and multiplied it by 3 right in there. And so I'm going to take my 44 times 3 and change the sign, so negative 132. So delta H is negative 132. So now, again, what cancels? The 3H2O gas cancels, so awesome. Okay? I still have one thing in my work down here that I don't want my final answer. I have those 3H2O liquids, okay? So I used equations 1, 2, and 4, so I need to now use equation 3. I need 3 H2O liquids over here on the reactant side to cancel those that I don't want, okay? So those show up in equation 3, but they're on the wrong side of the arrow, and they need to be multiplied by 3. So again, flip and multiply by 3, flip and multiply by 3 over there on the delta H. So if I flip this, it's going to be 3 H2O liquids on the reactant side, and the products are going to be 3 H2 and 3 halves oxygen. And my delta H is going to be that negative 286, change the sign, so positive 286 times 3, 858. Alright, so I think we've got it all worked out. We're just going to like double check now by, again, canceling stuff out. So I have the 3 H2Os that I wanted to go away. There they are on both sides of the arrow. Anything else that cancels on either side of that dividing line? 3 hydrogens go away. And some of the oxygen goes away. See how I have 3 halves over here? That's 1.5. So all of that goes away because it's the smaller amount. Over here I have 3 oxygens. Again, subtract out 1.5. And 1.5 or 3 halves is left over. Okay? So I'm going to switch to my highlighter and see what's left over. I have 2 borons. That's what I wanted. I have 3 halves oxygen. That's what I wanted. And I have B2O3 solid. And that's what I wanted. So my work adds up to give me what I want. So finally, I'm just adding up my delta H's to see what that final delta H is of the reaction. So 36 minus 2035 minus 132 plus 858. So our final answer is negative 1273 kilojoules. So let's write it down. Negative 1278 kilojoules. If I get rid of all this junk here, let's remember what it is we were actually answering. That's the delta H of that reaction, negative 1278 kilojoules. That is now a thermochemical equation. We have its enthalpy change and we have the chemical reaction. So that was a challenging example. If that one didn't quite make sense, that's what you'll see to practice on your homework a couple of times. So you will have some more practice with that. But most of them will be fairly easy, more along the lines of the earlier examples that we did. I hope this was helpful. Thank you for watching.